Assalamualaikum warahmatullahi wabarakatuh and good evening to my panel, Dr. Kamil, Dr. HADZLEY and Dr. MOHAMMAD. Today, I would like to present about my PSM1. Title of my PSM1 is Feasibility Study Toolware Pattern During Turning Titanium Alloy Under Air High Pressure. My name is Muhammad FAHRUL RAZMI and my supervisor name is Profesor MADYA Dr. Muhammad AMRI bin SULAIMAN. For introduction, based on background study, I found that titanium alloy are extensively used in many industries because of their high specific strength, which is retained at elevated temperature, as well as their fracture resistant and exceptional corrosion resistant. However, the measurability of titanium and its alloy is generally considered to be poor owing to several inherent properties of material. Due to that, the tool will worn out very fast and hence poor surface finish generate. In this study, a high pressure will be applied during the machining of titanium alloy, with the goal of identifying the cooling approach for most effectively and economically. The study will compare and evaluate cutting temperature obtained under various conditions. This project introduced an innovative and economically dispensive method that direct a high pressure jet to the flank, the rack, or both near the cutting edge. The expected outcome of this research is important since it contributes significantly improving the machinability of titanium alloy, hence improve productivity with high quality and dimensional accuracy of metal parts and products. For the problem statement of this project, the first one is characteristic of titanium alloy which low thermal conductivity, thus heat generated at the cutting zone, may contribute to wear progression on cutting tool. The second one is due to high temperature generated between workpiece titanium alloy and cold carbide tool may rapid tool wear progression because the cold material on carbide on tool which has contained titanium element such as chemical interaction. Therefore, to apply the air high pressure coolant may hope to lower the wear progression on cold carbide tool in turning titanium alloy. And the third one is in terms of cooling cost and hazard issue in handling coolant waste, this study will be focused on using air high pressure as coolant during cutting process. Air high pressure will be supplied consistently to the cutting area, thus reduce the heat generated. For the object for this project is the first one is to analyze the effectiveness of the air high pressure coolant in high speed turning titanium alloy, and then to investigate the surface roughness and tool wear mechanism on the carbide cutting tools. Also to develop mathematical models for tools life and surface roughness on the surface machine. For the scope of project, this project will focus on tool wear pattern in titanium alloy machining under air high pressure. The orthogonal turning experiment were carried out on CNC lathe machine. The experiment and collected data will be conducted in workshop Faculty of Manufacturing Engineering, UTEM. The tooling wear pattern will be observed for the analyzation to investigate the tool wear behavior and mechanism on various cutting speed value to live surface integrity of surface machine material and cutting temperature generated. The three main scope of project are conduct the data for experimental correlation of machining parameter with tool wear pattern, vibration, and surface roughness using Mitutoya SJ310, response surface methodology RSM, and ANOVA analysis. Second, investigate the effect of coolant on tool wear during turning in high pressure by using technique as high pressure coolant compressed air cooling. And then the last one is test and analyze performance of cold carbide during turning titanium alloy in a high pressure coolant. From the literature review, author Anurag stated in his journal Machining of Titanium Alloy from 2018 summarized that titanium alloy, a lot of machining difficulty occurs due to its hardness. Chemical reaction take place between tool and machine workpiece. High amount of heat generated at cutting zone. Also, Alderos Tina in journal Toolware in Titanium Machining from 2012 state that turning titanium alloy with WC/Co cutting tools at cutting speed 30 to 60 meter per minute causes chamfering of the cutting tool's edge and addition of built-up layer of workpiece material on top of the rack face wear length. And Journal of Coating Performance on Carbide Insert by Narasimha from 2014 summarized that the performance of carbide insert found to be better while compared to that of uncoated carbide insert under dry machining. An investigation of cooling and lubrication strategy for machining high-temperature alloy by Katja Hotchmuth from 2016 summarized that high-pressure cooling enables good chip control, a reliable machining process and reasonable to life. And then the last one is high-pressure cooling in the machining of hard-to-hard machine material by Davorin Kramer from 2009 summarized cooling with high pressure in rotating operation is an effective method for giving higher productivity, reducing temperature in cutting zone and increase chip control as well as control the lifespan of the tool point depending on the pressure and flow rate of the fluid jet. For the methodology, machining tests were conducted on a CNC lathe that has a continuously variable spindle speed, CNC lathe capabilities and its specification shown in table. The cutting speed are set at 120, 170 and 220 meter per minute, while that feed rate are set at 0.1, 0.15 and 0.2 millimeter per revolution and depth of cut at 0.4, 0.5 and 0.6 millimeter respectively. The experiments are carried out in a high-pressure coolant using coated carbide and response surface methodology (RSM). The second method is using Mitutoyo SJ310. From the Mitutoyo, we can measure the surface roughness. Surface roughness is the measure of the finely spaced micro irregularities on the surface texture, which is composed of three components, namely roughness, waviness, and form. Surface roughness measurement is important to measure the surface finish of the workpiece and quality of the parts. To get the better surface finish, the suitable process is required to maintain the quality of component. The third method is a high-pressure coolant. This type of coolant is used during in machining process. Air, water vapor, carbon dioxide, oxygen, and nitrogen are the primary gas used in this device that are contained in the compressor. The compressor are method require the use of a compressor to compress the dry air supplied by a nozzle in the cutting region. This method is used to reduce cost and the low environmental effect of air and water vapor relative to other make them especially desirable for us. The fourth one is titanium alloy, extra low insertion. The material chosen for machining test was titanium alloy with 32 HRC/317 hardness weaker and additional with extra low insertion. The titanium is cylindrical shape with the diameter is 100 mm and length is 150 mm. The workpiece installed the chuck central applied at the base of the workpiece. To reduce the vibration by the hole are held by the tailstock. The fifth one is coated carbide. We use coated carbide throughout the cutting process. Carbide inside insert of ISO designation CNMG 120-408 MF115 will be used. The cutting used is coated carbide, stainless steel, and super alloy. The tool is type of diamond shape and tool featuring high precision coolant for excellent chip breaking with code. The last method is design of experiment. The combination of cutting parameter will be arranged by using response surface methodology (RSM) and 17 of experiment will be arranged by box Behken in RSM. From this table, the obtained data were analyzed in order to investigate the relation of surface roughness and parameter. For the figure on the right, those are the flow chart for this project. Figure 1 is the overall flow chart, while figure 2 is the experimental flow chart. Thank you for your time. I'm looking forward for Q&A session. Assalamualaikum.